How's it going, everyone? Today we're going on a bit of an adventure and we're going to look at two different integrals from, I guess, two ends of the mathematical spectrum. And at two vastly different price points, we're going to compare them and see which one gives the better experience. Now, I'm not alone in doing this. I've enlisted the help of someone with very fine taste in mathematics, and that's Jens from the channel Flammable Maths. Now, Jens is a seasoned integral taster, so he is going to walk us through today's delicacy, an integral which requires complex analysis. To start with though, I'm going to walk us through today's budget item, and it's an essential tool in the toolbox of any budding mathematician. Today I'm going to be integrating everybody's friend e to the x. Now, I'm working at what is essentially a poor man's version of a blackboard today. It's a sticker on a wall with lots of bubbles, but you get what you pay for, I guess. Now, e to the x is a function that was almost designed to be integrated, or to be more particular, designed to be differentiated. E to the x is a creation of mathematicians. We made e to the x because we wanted a function, call it y, where the slope of y at every point was equal to the function itself. Now, this is satisfied if y does equal e to the x. We can have a look at how y, or e to the x, would be constructed, and let's first think about where it would start. So if we wanted to start at x equals 0, then this is e to the 0, which is 1. So y at that point is going to be equal to 1. All right, so let's write down and construct our y of x. We know it starts at 1, and we know that the derivative of it, dy dx, is going to always be equal to the function itself. So that's going to have to start with a 1 as well. Now, this is also the derivative of this, and we know that for a 1 to be in the derivative, it means there must have been at least one function of x in the function itself. So if we have 1 plus x, that will correctly give us the derivative 1. But in doing that, these are no longer equal anymore, so we've got to make them equal. Let's add that x down here as well. And that gives us the same problem. To have an x in the derivative of a function, there must have been at least an x squared power in the function itself. In fact, it would have had to be x squared over 2 to give us this derivative. But, we need to keep these equal to each other, so we're going to have to add that term here as well. We seem to be going around in circles a little bit. Then this is going to keep going on like this. You might recognize the pattern to actually be x to the n over n factorial, where, for example, here n was 2, this is 2 factorial, it's just 2, and we've got the squared power up the top. So this here, and this keeps going, this is going to be our series representation of the function e to the x. That's what it's equal to. Now, you might be familiar with e, the number, as being like 2.7 something. That pops out of here too if we were to set e to the x with x equal to 1. If x is equal to 1, this is just e. And if that's going to be always a 1, this would be a 1 here. This would be 1 squared over 2. That'll be a half. So that's already 2.5 there. And each of these smaller terms are going to, get to be very small numbers. We're going to keep adding on successively smaller amounts until it, gets to around the value of 2.7 blah, 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 blah. All right, and that's the familiar face of e that you might have seen before. This is a way of writing it out that shows you in a way how e came to be. It was designed so that the derivative of the function was always going to be the function itself. Using the property of e to the x that we just went through, we can write down its integral as e to the x plus our boy c. Now, if you've done almost any integration at all, you'll remember or you'll recognize what c is. He's our friend that we just have to remember not to leave behind. He's the constant of integration, and he's there because, you know, he doesn't depend on x, so the derivative of the c would have been 0, and so it's very possible that there could have been some constant here where when differentiated it disappears. So we've got to leave that there just in case. But this is our integral. Pretty basic, pretty intuitive, and very widely useful. So when tasting integrals, we've got to consider multiple things, such as the value, the complexity, the beauty of the integral, and, you know, its usefulness. And I'd say this one scores pretty highly. I think it's, you know, got a big bang for your buck. You're getting a lot of value out of this. You can use this integral in a lot of places. It'll make math pretty simple for you, and it's pretty elegant as well. So I'm looking forward to seeing what our next integral looks like and how it can rival this one here, but let's hear from Jens on that one.
Good morning, fellow shrimps. Thanks to Toby for inviting me to her little show right here. But Toby, are you serious? That's not what I signed up for. Take a look at that. I can't integrate this. I just don't feel worthy. I physically can't integrate this function right here. What the hell do you think you are giving me here? I'm out. So my manager just talked to me and he told me if I don't integrate this function, then I'm gonna be fired. So I guess I have no chance right here. We are going to give this thing right here a shot using complex analysis today, because that's just really elegant. And you see that's the function, and we are going to call this thing I for integral. You can also call it J for Jens. I really don't care, or T for Toby. And at first I would like to define a complex function, a complex valued function. We are going to call it f of z, and we are going to define it as follows. That's natural log of z squared over z squared plus 1. And if you take a look at the denominator right here, what is plus 1? That is nothing but negative I squared, where I is the imaginary constant. And you see that's just the difference of two squares, and we can factor it, so that's quite easy. So we end up with natural log of z over z plus I times z minus I. And this denominator right here gives rise to two poles, two singular poles at that. So where are our poles at? They are part of Western Europe, I know that, but also we can just take a look at here. So poles are just points where our denominator would go to 0 and our function would explode to infinity, you could say. So that also means we have two poles, z1 and 2, at the points I and negative I, so plus and minus I. And now we can take a look at the contour, because if we want to use the residue theorem, complex analysis, we would like to take a look at the contour integral of this complex valued function f of z integrated with respect to z. Okay, that's cool, but what does our contour look like? Well, for this I would like to take a look at the complex plane, and just at the upper half, so this makes things easier. So why not take a look at a semicircle in the upper half of the complex plane? But here's the thing, we have a singularity, you could say. If we plug in 0 into here, in this natural log of z, this function would explode to negative infinity. We don't want it, so we have to get around the singularity. That's a branch point, so why not construct a little semicircle around the origin right here with a little radius of epsilon, I don't care. And our outer semicircle has a radius of r. So this goes from r and negative r right here to negative epsilon and epsilon, because epsilon is just the radius. And this thing right here is just the contour, C. That's what we are going to call it. And also, our outer semicircle is nothing but gamma. We are going to call it this. And our inner semicircle is nothing but, I don't know, capital lambda. So that means our contour integral right here consists of 4 parts. We have this gamma integral, and then also we have this lambda integral. And also we have 2 other integrals. One on the real axis. So here we are going to integrate with respect to z, but those are just running on the real axis. So we have another integral running from negative r to negative epsilon f of x dx. So just changing those complex valued sets right here to just real valued x's. And also another integral from epsilon to r of the same thing, f of x dx. But also, like I said before, we would like to use the residue theorem. So those four parts added together are equal to 2 times pi times I times the sum of the residues in this case. But we only have to consider one residue because our contour just has the residue of I in it. So this singular pole I. So Z1 right here, the residue at the point Z1. And we're going to calculate it now. You might ask yourself now, what the hell is the residue at the point Z being equal to I? Well, we boys here at BuzzFeed are going to do it that way. We do nothing but apply the limit when Z approaches I to Z minus I times f of z. But what exactly is f of z? It's nothing but the natural log of z squared over z plus I times z minus I. And you see this is going to cancel out quite nicely. That's why we factored it in the first place. And well, now we can just apply the limit without any complications. So we have the natural log of I, complex number, that's weird, squared over 2 times I, because I plus I is just 2 times I. You might ask yourself now, what exactly is the natural log of I? Well, we can just take a look at the complex plane for that. So this right here is the complex plane, with this being the real axis, and this being the imaginary axis. And where exactly is our point I? It's just up here. And if you take a look at the definition of a complex function, z is nothing but r times e to the I phi, where r is the length of our vector right here, in R2 you could say, and phi is just the angle enclosed by this vector and the real axis. So that means if we just go up here to I, what's our angle? Well, this is pi over 2. But now you could say, what if we go around this way once again and land here? This is just 5 times pi over 2 and again with some k times pi over 2, k of some integer number. Well, we are just going to take a look at the principal branch right here being pi over 2. We're just going to do that. We are not making it more complicated than it already is. And what exactly is our r? Well, it's just length of the vector, but I is on our unit circle, so that means r is nothing but 1. So that also means that I is nothing but e to the I times pi over 2. And if we apply the natural log to both sides, natural log of e to the something is just this something itself, so I times pi over 2. And here we go, we are done, and we can plug this in. So we end up with I times pi over 2, but the whole thing squared over 2 times I. And well, I squared is nothing but -1 times pi squared over 4 times 2 times I, so this is 8 times I. And now we can just plug the value of this residue into our contour integral, and then we are basically done. So all I really did was just plug everything into what we have gathered before, and you might notice on this expression right here our I is going to cancel out, so that makes it real valued, that's cool, and our 2 and 1 over 8 is going to cancel out somehow to 1 over 4. So we end up with this additive chunk right here to be just negative pi to the 3rd power over 4. Okay, that's cool. And now I would like to take a look at only this integral right here. So we are going to write it out. Okay, we are going to end up with an integral from -r to -epsilon of natural log of x squared over x squared plus 1 integrated with respect to x. And well, what we can do now, we can just introduce a substitution. So let x be equal to -x or -u, you can call it whatever you want, it's just a dummy variable. So what we want to do, we want to let x be equal to -x. That also means that our dx is going to be transformed to -dx, and we can plug all of this chunk in. So what happens to our upper and lower bound? Well, they just change signs to r and epsilon in this case. So we have natural log of -x, natural log of a negative number, that's weird once again. We're going to talk about this in a minute. Over, well, -x squared is just x squared, it doesn't change, plus 1, -dx. And now we can distribute this negative sign into here to change the order of integration into the integral from epsilon to r of the natural log of negative x squared over x squared plus 1 dx. And for this natural log of a negative number, I would once again just like to take a look into the complex plane. Let's put it here. So just like before, we have talked about the vectors before, so z being equal to r times e to the I phi. And on the real axis, our negative 1 is right here. So that means we are going to go this way, and we are enclosing an angle of pi in this case, taking the principal branch once again. And also it's lying on the unit circle, this negative 1, so our r is going to be 1. That also means that natural log of negative x is nothing but, well, we can use the natural log property because this is just negative 1 times x, so turning it into the natural log of negative 1 plus the natural log of x, and well, natural log of negative 1 in this case, so negative 1 is nothing but e to the I times pi, taking the natural log on both sides, it's just I times pi. It's as easy as it is. So we end up with I times pi plus natural log of x. And we can plug this new information into here. So we end up with, let's put this in the box, the integral from epsilon to r of the natural log of x plus I times pi, whole thing squared, over x squared plus 1, integrated with respect to x. And you see, we can just use the binomial formula up here in the numerator to end up with a final integral from epsilon to r of natural log of x, whole thing squared, plus, and now natural log of x times I times pi, and now I times pi squared, this is just negative pi squared over x squared plus 1 dx. And I'm going to write everything out, and I see you back in a second. So as you can see, I just wrote everything out nicely, and do not wonder about this expression. That was just the integral we had derived a second ago, but broken up into 3 different integrals. Since those are just additive, we can just break them up. And now I would like you guys to consider something. And girls, also the girls around here on this channel. If we would just let epsilon go to 0 in the limit and r go to infinity in the limit, well, that would just be our original integral that we wanted to evaluate. Same thing here, so we can add those two together in a minute. But what exactly would happen to, for example, to this gamma integral and this lambda integral? Well, we are here at BuzzFeed, you know, and we have a lot of money, so the ad revenue is falling from the sky all day long. But what we don't have is a lot of time. That's why we went to our local complex analysis dealer, you know, this guy that is selling you lemmas and theorems and stuff like this, and we bought a little DLC called Jordan's Lemma, and we can use it on those two right here. All it really does is to let the lambda integral go to 0 in the limit when epsilon approaches 0, and if r approaches infinity, gamma is also going to 0, so this makes things really easy, and we are going to take the limit on both sides now and see what we get. So we end up with the limit as epsilon goes to 0 and r goes to infinity of our contour integral. I'm going to write it like this. This is just on this side right here, well, this is just the limit of a constant. It doesn't affect our constant, so negative pi to the third power over 4 being equal to this and that is going to vanish. We can add those two together, and I want you guys to notice and girls to notice, I'm so sorry, this needs to be politically correct. No, I have no idea. But if we let epsilon approach 0 and r infinity, that's just our original integral I. So we have 2 times I plus I times pi. And this one doesn't really concern us. We are just going to call it j now. It doesn't really matter. So this is just j, like Jens the mathematical meme guy, this is probably me. And also this integral, negative pi squared times the integral from 0 to infinity of dx over x squared plus 1. And you see, this right here is really easy to evaluate. This is just the inverse tangent, this integral right here, of x in the limits from 0 to infinity. And well, inverse tangent of 0 is just 0, and the inverse tangent when x approaches infinity is just pi over 2. So this is just pi to the third power over 2. So what do we have? We have negative pi to the third power over 4 being equal to 2 times I plus I times pi times j, negative pi to the third power over 2. And what we can do, we can add this expression on both sides. So adding pi to the third power over 2. Also here, pi to the third power over 2. This is going to cancel out. And this thing right here is exactly going to evaluate to the positive term right here. So you can advance this fraction by 2 over 2. And you immediately see where this comes from. So this is just pi to the third power over 4 equals to 2 times I plus I times pi times j. And since 2 isn't equal to 0, you can prove this by using piano axioms or something. Or you can just trust the BuzzFeed guy right here on this. We can divide both sides by 2. So this by 2, this is going to cancel out, this by 2, and if we divide this by 2, this is just pi to the third power over 8. And you see, the real part of this complex number, so real part, imaginary part, is just going to be the value of our integral that we wanted to evaluate. So that also means the real part of this contour integral, f of z, dz, contour integral, is nothing but pi to the third power over 8. So if we just compare coefficients, you could say, and this is nothing but our... We are done, my boys and girls and everything else in between. The value of our nice little contour integral right here is pi to the third power over 8. And this thing is worth $1 million, probably, because it's just so damn cool. Complex analysis is awesome. And if you did enjoy this video, please like and subscribe to the shrimp and me. I'm Flammable Maths, if you didn't know already. And up until the next video, have a flammable and Tibees day. See ya!